So, good morning everyone. Welcome to lecture 11, I believe, of Introduction to Programming. So, in the last class, we have looked at C functions, and I kept on repeating that C functions are not really mathematical functions, and probably we will see that why they are not always a mathematical function. But today what we are going to do is that we are going to talk about recursion, so recursive functions, and we will see that actually many students are scared of recursion, but recursion comes quite naturally in computation, and there are programming languages where it is the correct way to sort of loop through things. There is no explicit loop. There are programming languages like that. So we will talk about recursion today, and we will also see that why C functions are not mathematical functions, at least not always. Okay, so let's start. So I think that what I'm going to do, so let's talk about mathematics first. So you might have encountered recursion even in mathematics. In your school you might have studied certain functions. So for example, let's take a look at this function sequence, this function, and many times the functions are defined in this manner. So this function is equal to, we'll say that if it is 0, if n is equal to 0. So you might have seen such definitions in mathematics. It is 1 if n is equal to 1, otherwise it is so I don't know how many of you have seen such function. You might have actually seen this thing but with a different name, so it is popularly known as Fibonacci sequence. Right, but the reason I am writing VIR, because these numbers were discovered much before Fibonacci by an Indian mathematician called Virahanka. They are also called Virahanka numbers. You can look it up. So I think it's about time that we start giving credit to the original discoverer of this sequence, right? So what does this sequence tell you? So you know that if, for example, and this is from the function is from natural number, or if you are confused that whether natural number includes 0 or not, you can always do this and this too. Right, so this is your function. Right, so the series goes, the 0, 1, 1, 2, 3, 5, 8, 13, and so on and so forth. And you see that here, I am not explicitly saying that for any arbitrary n, how to compute the value of this Virahanka n. I am saying that I only know this much, that how to compute what is the answer if n is equal to 0, what is the answer if n is equal to 1, and for others what I can do is that I can reduce the size. So you say that here the argument is n, and whereas here the argument is n minus 1 and n minus 2, and you say that, and then you recurse. So this is a function, this is a mathematical function. I am defining a mathematical function as a recursive way, that it is the same function I am invoking with in some sense a smaller argument. Okay, let's look at some more examples. So we just I think in the last class we discussed factorial. Right, so what is factorial? For factorial also we can say that it is 1 if n is equal to 0. Otherwise factorial n minus 1 into n otherwise. Right, so I can say that when n is equal to 0, I know the answer is 1. Otherwise what I'll do is that I'll multiply n with whatever the value of this function at this point n minus 1. Not only factorial, in fact many computations. So let me just say that let's say that I have a function called successor function, and what this successor function does is that it just adds 1 to whatever the argument that is given to it. Okay, so let's say that I have only this. Now using this I can build much more advanced mathematical operations, right? Mathematical functions I can define. So what I can do is that I say that, let's say that I want to do addition of two numbers, and I say that this addition, I'll say that the answer to this addition is n if m is equal to 0, which is sort of quite straightforward, right? That basically if you add 0 to something, then you get back the same number. But if, for example, if m is not 0, then I can say that okay, then the answer to this is a successor of addition of m minus 1 n. Right, otherwise. And now the successor function, I know that what it does, that whatever it is going to just add 1 to it. So here you see that even the addition, I am defining it as a recursive application of increment or a recursive application of successor operation. Right, there are many more functions, so let's discuss. And I think that if you are up for it, what I suggest that, for example, now that you have addition, what about multiplication of m and n? Let's just talk about positive or non-negative integers for a moment, right? So how do you define multiplication of m and n as a recursive this thing? So here you can say that okay, so this multiplication of m and n, you have to say that it is 0, and this is if you want to do a kind of a shortcut. So we'll say that it is 0 if m or n if m is equal to 0 and this, or n is equal to 0, is equal to, I will say, let's say n if m is equal to 1, and this is just a shortcut. I don't think that I have to do this particular part. I will say m if and the last part is what? So basically none of them are 1, then I will say that this is nothing but, so multiplication of m and n is I am adding number m n times. So I will say that add m to whatever, so I am adding it 1, so now I only require m to be added n minus 1 times. So I will say multiplication m n minus 1. In fact, yeah, so since I am reducing the second argument, I don't even need this. The first argument is not reduced. This is probably not required, the second one, right? So otherwise, remember that we are not talking about programming, we are talking about mathematical functions, but you can see that quite a lot of mathematical functions, they come very naturally, they appear very naturally in mathematics and also in computation. So for example, if you want to evaluate that what is the value of this function on some points, if you do not know directly multiplication, I give you this definition that this is how I am defining my function, and the addition is defined like this. So you see that the complete definition I have only given you for successor, that you know just add 1 to it. Rest everything is built on top of the successor. So when you expand it, essentially the multiplication is calling, you know, multiplication is recursive, then addition is also recursive, and finally it's all called to successor functions, nothing else. Right, we can do just one more. So now that we have multiplication, what I can do is I can do power, right? So let's say that power m and n, we are only talking about non-negative integers. So let's say that, you know, for the sake of this function, we'll just assume that so both of them cannot be 0, because 0 to the power 0 is not really a defined entity in mathematics. So let's just, you know, for the moment assume that we don't want to get into those things. Assume that m and n both are not 0. Okay. In fact, you know, just for the sake of simplicity, I'll just say that m is not 0, right? So let's say that m is not 0. Okay, so we know that the answer to this is 1 if n is 0. That anything to the power 0 becomes 1, and we certainly know that m is not 0. So now what is it? So power m to the power n is essentially multiplication of m with m, and this is done n times, right? So if n is any other value, or I'll just say that, okay, if it is m, if n is equal to 1, so this is also fine. So now we know that the value of n is at least 2, and now what I can do is that I can again recurse on this power. So I can say that, okay, I don't know power m power n, but I know value, if you know, if the value of n is small enough, so I can do is that I can try to reduce the second argument by saying that, okay, I know that this is if I multiply m with whatever the answer to power m n minus 1. So now you see that the power function is also defined recursively. So I am reducing the second argument, and I know that again under this assumption that m is not 0. So please think of that, you know, all the way to the power, we have everything finally boils down to that you are just calling the successor function, because power is calling multiplication, multiplication calling addition, addition is calling successor, and it is all repetitive application of successor function. This entire computation, all of this is built on top of just one argument, that, you know, you have the ability to add 1 to some number, right? Just a successor function. So you see that recursion comes very naturally, but one common pattern that you will see in this recursive formulation is that there is always these conditions, right? So these right, so these are sort of, you know, terminating condition, all of these. Here, if I go back here, it is this. Right here you can see that this is a terminating condition. Here this is terminating condition, and this is quite essential actually, because if imagine that I give you something like this, let's say some number foo n is equal to, I say that n plus foo n minus 1. Now let's say that I say that okay, this is a mathematical function, I am defining it like this, and you will tell me that well, this does not make any sense. There is absolutely no possible way to evaluate it, because okay, you are saying that if it takes some argument n, I have to add n to foo n minus 1. So this is what I mean. This is some n plus n minus 1 plus n minus 2. It can just keep on going. So yeah, this is kind of weird. So you will say that okay, this is problematic, right? We don't want such infinite sequence of numbers to come, because evaluating that is see, sometimes infinite sequence do converge in mathematics, but the thing is that in computation you want to have things finite, right? It's not like if you want to evaluate some particular argument, then you don't have infinite steps, right? That means that if you have infinite steps, that means that you have to wait for infinite amount of time if you want to actually do step-by-step computation. Even though there are convergent series in mathematics, you still don't want to do that, right? So in one of the lab exercises, I think that there was an exercise given on Taylor series expansion. In Taylor series also it have infinitely many terms, and the more terms you take, more precise your answer becomes. But you know that in computation you have to take finite amount of terms. So this part over here, the part that is in this red, this is very important. You always have to ensure that when you define a recursion, it kinds of terminate. And we will see that this is something similar to saying that so recursion and loop are kind of equally powerful. So if you have infinite loop, similarly if you don't have such conditions, that means that then what you will have is something like this, which is an infinite recursion. This recursion does not terminate. In fact, if you have infinite recursion, what's going to happen is that in the last class we spoke about stack frames. So one function will keep on calling, putting another frame, etc. Keep on pushing new stack frames on top of the stack, right? So let's say that this is the frame for foo n. That guy is going to call another instance of foo on n minus 1. That guy is going to call instance of foo on n minus 2. And this is just just keep on growing your stack until you run out of memory. You literally will run out of memory. You can try it on your computer. I don't want to do that right now because there is a very likely possibility that your computer will hang and you might have to reboot your computer. So in the live class I don't want to do that, but you can certainly you have all other applications closed, and then you can try such a program, and you will see that this will be an infinite recursion. It's going to run out of memory at some point in time. So now that we know that recursion is nothing to be afraid about, it is just that I have a bigger argument and somehow that argument has to reduce. It's like a mathematical induction, right? So let's go to our program. Let's take a look at so now again, let's say that what we want to do is that we want to write a factorial function again, but this time we will write it in terms of recursion. Now I don't, so so this is just for example, factorial, since it can be computed via loop, it should be done via loop, because the computational overhead of a loop is much smaller as compared to calling a function, right? Because it has to have a stack frame, you push and all these operations. So computationally it is much more faster to write loop if you can, but if you can't, then you should use recursion, and sometimes the control flow becomes much more easier, it comes much more naturally with recursion. So in that case it might be easier to use recursion, right? So now I'm just going to take an argument. Now the very first thing is that I need to have, you remember the terminating condition, right? If you forget that, then it will run out of memory. So I'll say that if num is equal to 0, then return 1. Otherwise, and I can write else, but there is no need to write else, because now the only thing is that return num star factorial num minus 1. I can just do this. And now let me just try to call this function. So let's say that value of the factorial is I always keep on forgetting new line, so let's just put new line first. And yeah, I think that we'll run it a couple of times. So let's scan a number. And yeah, so let's hope that this works. Because I keep making many times syntactic errors. So GCC -o. Okay, wow. And now it is waiting for us to ask for recursion. So verification of factorial is this. If I put 0, it should print 1. And let's say 5 and 6, and you will see that after some point in time, if you put the large enough value, then you are not really sure that whether that value is yeah, right. I mean, so 100 factorial, it says that it's 0 because of the overflow. Okay. So recursion is not very hard. It comes much more naturally. In fact, many times when writing a loop is difficult, writing a recursion is much more easier. So now let's talk about composite types. So in C allows you to define new data types, new types based on, so you can take some built-in types like int, float, etc. and it allows you to define new types, right? So let's say that, for example, I want to define a point. So you know that point can have x coordinate, y coordinate, so in the xy system. So I can define a new type like this. And if I want to define a variable of this type, so this is just defining a new type. I'm using _t to indicate that this is a type, and I'm not the only one. So even if you look at, like in C standard, there are types like size _t, uint 32 _t, etc. So this _t is something that is not mandatory, but it's a good convention to use to indicate that something is a type. And now I can use that point. So what I can do is that I can say that point _t p1, in this you can initialize using the initializer list. So you can say that let's say that this point is 1.0 and 2.0. And now if I want to print, since there is no way to directly print the point, in fact, so let's say that you want to directly print the point. So then what you can do is that print point. You can define your own function. Now that we know that there are functions, so what it does, it takes argument and now you can print the point, right? So %f. And the way you, so for example, this is a variable p of type point underscore t. So how do I access this one particular field? So these are called field or member variables. So if I want to access the field of x coordinate, I'll say p dot x. So this is a new operator. And similarly the second argument is p dot y. So this is going to print my point. So I'll say print point p1. And I'm hoping that syntactically everything is correct. So you have to say that this is a struct. Yeah, I think that was the mistake, and similarly you have to say that this is a struct. So I think this part was fine. Yeah. Okay, so yeah, my apologies. So this is how you define. So every time you have to say that this is a composite type. Yeah, let's first run this program and then we'll see that how to make it better, a little bit more readable. And then now if I do, then it printed 1 and 2, right? So that's what it did. Now you see that this is the problem, that every time you have to write struct, then the name of the type, and then you can declare a new variable. But instead what you can do is that you can, so there is another construct for type alias that is called a typedef. So I'll write So here what I did is that I created a type alias. So it created a new type. You remember that any enum, if I declare, that is a type alias for int. Now this is another type aliasing mechanism where point underscore t is a type alias to this struct underscore point underscore t. So what is the advantage of doing that? The advantage of doing this is that now I can just use point underscore t because it is a type alias for this underscore point underscore t, and that is how it is behaving. Right, so and this typedef you can do for a lot of other things. So let's say that what you want to do is that you want to have a triplet, right? A triangle, right? 3 points. So that means that 3 points are required, and what I can do is that I can declare an array. So I'll say that typedef array of these points. So I'll say struct underscore point underscore t, and I declare a new triangle type with 3 points. Now this is not many people are familiar with, that you can do this with typedef as well. So it's a triangle type, and the array size is 3. So now if I declare a new variable for this triangle type, then it will automatically declare it as an array of size exactly 3, nothing else. Okay, so let's say that, for example, let's declare a new, so I'll say triangle underscore t, and now we know that I can initialize arrays, but every element of the array itself is what is a point, right? So that means that there are 3 points, and every element you can initialize. So let's say that 1.0, 2.0, and then let's say 0.0, 1.0, 0.0. I think that we can just print the points of the triangle here by saying that print point. So I already have print point, so I'll say 0. Right, so it printed all these 3 coordinates. So what is the syntax? The syntax for typedef is you write, this is a keyword called typedef. You write the name of existing type, and then you define that name of alias. So then this name of this alias is going to, it just creates a new type alias. It's going to behave exactly the same way as this one. Right, so that is what the syntax of typedef. It does not create a new type, but it just creates a type alias. So this is a, whereas the struct, right? So struct keyword. So what is the syntax? It is a struct, and you give it a name. So then struct space that name, that whole thing is a new type. Now what is that type? That type is float cross float. So these are the possible values that it can take, right? Set cross product, so it has 2 floats inside it. So it is float cross float, that is the set from which the values of this type is going to come, this new type. So struct creates a new type, whereas typedef creates a type alias. And so this, many people don't know that you can use typedef with arrays. So when you give it a size of array like this over here, that automatically fixes that size of 3 for the array, and it comes much more naturally. So you see that now this code looks much better by saying that not only that I'm saying it's a triangle, but since triangle is a 3 point, I fixed those 3 points. So now I can just declare a new variable called triangle, and it will just have exactly 3 points, nothing more, nothing less. So this typedef allows you to write much more readable code, much more expressive code. It's much easier to read that it's a triangle, otherwise saying that you have to create a array of size 3 for points, and then somebody tomorrow, if they use some different size, it's a problem. So you say that, okay, no, this is a new type alias for triangle. What is a triangle? It's just an array of 3 points, array of points of size 3. Okay, so we have learned struct, and you can do anything, by the way. So you can not only float, you can mix float and int and any other type that you like. So for example, you can have struct student record, and let's say that student record has a name. So character name 10, or even better yet, now that we know that I can use, so I'll say that it is character Now what is the benefit of this is that I say that okay, I want to allocate 10 characters or let's say 15 characters for the name. Later on, if I want to change the number of characters required in my program, I just have to make this change in one place, not everywhere else. And here I can now just use name underscore d name. So student has a name, and since I want to make a one particular point, so I'll say let's say struct. So let's say that the student has a height. In fact, we'll say that height in centimeter, and height cannot be negative, so we will write height. And similarly, let's say that weight in kg. Weight also cannot be negative. And I can now define a typedef for this. So let's assume that there are no fractional weights for a moment, right? Because I want to do something with this. So now we'll say that okay, in the student record, what you have is name. What you have is height in semi, which is h. We'll say that weight in kg, which is weight. And in fact, now this is also another nice this thing for enum is you can now say that, let's say, blood type, right? So here you can say that blood type is blood type. You see that now with all these type aliases coming together, you have now student record, and if somebody reads student record like this, you immediately know that okay, there is some name, there is a height in centimeter, weight in kilogram, and then there is a blood type. And now see, one thing to notice, so I think that we looked at that in enumeration. What used to happen is that color, and you remember the example that I can assign a color to a day of the week, which does not make any sense. But the problem is that because enum creates a type alias to int, any operation on int, so you can assign one int value to another int. That is all possible. But here you will see that that is not the case over here. Okay, so now let's we'll remove all of this. Print student record. So void is, by the way, another keyword when you don't want to return anything, when you don't want to return any value. And this is going to be and now let's say that I want to print name of this person, which is person S. Then height was what? Percent u, right? Percent u and percent. I have to do a switch case, but I'm just going to write this number over here. I don't want to waste time in this. And how do I access the field? So it is sr dot and you see that now it is a name. So I can just say that it is a name. What is a name? Name is just a character array. I think that I have defined it like this. So it's going to print a name. The second argument is sr dot, and it is h dot height, I think. Why h dot height? Because you remember that even this height in centimeter t itself is a character. So it is a one structure is nested inside another structure, right? And I can have sr dot w dot weight, I believe, and then sr dot bt, I think. And you can initialize this student record again as a, you can initialize via this initializer list. So what was it? The first was the name. So let's say that it is something Bob, and now height. So in fact there is a structure inside again, and technically what you should try to do is that again add parenthesis and then initialize the field inside the nested structure. So I'll say that that person, let's say that have 170 centimeter height, have let's say that 70 kilogram of weight, and blood type is, let's say, A positive, because so it will come out as 0 over there. And now what I can do is that I'll just say student record sr. What did I do? It should be in main. Okay. So yeah, just like you have to put struct everywhere, just like a struct. I have to again, whenever I'm using this blood type. So what I'll do is that I'll do this and then define yeah, so at least this should fix the blood type issue. Yeah, okay. You have to write in here, that's the whole point of this. This is what typo does. Wow, such a small typo and such a big price to pay, right? Okay, so now, yeah, I'm hoping that the print student record should print. My computer is damn slow right now. Yeah, so Bob 170, and since it was A positive, which was 0. Okay. So there are this whole reason why I created. You see that one very obvious question. This whole exercise I did is one very obvious question is that why did not I directly write unsigned height and unsigned weight here inside this struct, right? I can just write unsigned height, unsigned weight, and yeah, that also can be done. There is nothing wrong with it. But you remember that in the enumeration, if you remember that I was able to assign colors to weekdays, I was able to multiply color with a weekday, etc., and all of this, which doesn't seem natural, but the problem is that all of this creates a type alias. Now let's say that I height in so let's say that h1 and this is an integer, and I'll do this, and let's say weight in kilogram, w1. These are all structures, right? So I do this, and now let me try to assign a weight to a height. You see, the thing is that both of them, both height and weight, both of them have exactly one unsigned integer inside it. So as far as the set of values are concerned, you please remember, right, I said that types are in a very, in some sense, set of values combined with set of operations, right? So the set of values are exactly the same. It is the same set that both of them will draw its values. So struct will create a new type. Typedef creates a type alias. Now in this new type, you see the set of values are exactly the same. But now let me try to do this thing. This whole exercise I did just to show you what happens now. That I am trying to assign a weight to a height, right? And see, and this is precisely why we did that. So they are saying that incompatible types when assigning to type height in centimeter t from type weight. It created a new type. Not only it created a new type, that type is incompatible with other types, even though the set of values are exactly the same. If I have 2 unsigned and 2 unsigned over here, that does not mean that I can assign one to another. Now, why did I do that? And see, if I had just done, unsigned height, unsigned weight, it is possible for me to assign a weight to a height, or assign a height to a weight. But because I have embedded it inside a structure, now the type system of C. So what is the type system? Essentially, there are these, what constraints that the compiler and the runtime enforce on what you can do and cannot do on certain types, right? So now the type system ensures that I cannot do that. It's a illegal operation. And many times, if you want to write safer programs, this way of writing program is better, right? Because you are making use of the type system to help you write correct programs, to help you write safer programs. And you should allow type system to help you by doing this. So now it says that, sorry, you can't assign a weight to a height. That does not make any sense. But if you remember in one of the earlier lecture, I was able to assign a color to a weekday. That does not make sense, because we write programs to capture and do computation over what we observe in day-to-day things, and we want to automate those things. And over there, you can't assign a height to a weight. That does not make any sense. And that you can do in C by saying that, okay, they are different structure. It creates a new type. So even though the set of values that it takes is the similar, they are not compatible types. The compiler will prevent you from doing so, because the standard forbids this. So this was the point of doing this. So we have looked at a lot of things. We looked at struct, and you see that I can also do give names. So it doesn't. So right now this is in exact the same order as this one: name, height, weight, and blood type. But if I want to change the order, I can specify by its name. So I will say BT is equal to, let's say, B positive, and like this. So I can just give a name, then I have to give name to everything. So I'll just say name is equal to this. Let's say that I'll write dot W is equal to 65. Let's say, and dot H is equal to 170. Dot BT, dot H, dot W, and dot name, right? So these are in like different order as compared to what is specified in the structure. If you don't want to specify the explicitly fields, then you have to put it in the same order. And again, let's hope that I didn't make some silly mistake, so that my compiler, yeah, so this is the same error, so this is fine. Right, so Bob 170, 65 and 1, because it was B positive. So we have learned recursion. I hope that, and one very nice exercise to do now that you know arrays and now that you know recursion is that I would suggest that you do this exercise. It's a very fun exercise to do. Is let me just write problem and then my computer is damn slow today. Okay, so those of you who know chess, this exercise has nothing to do with your other thing. If it is posted for the lab, then all of you have to do it. Otherwise, all of you know chessboard, right? This is a very bad drawing of chessboard, 8x8 essentially grid. And now what I tell you is that you place 8 queens so that no queen is attacking another queen. Okay, and using recursion you can do this in a very easy fashion. So now you know multi-dimensional arrays, so you can represent this 8x8 grid, and you can use recursion. So you can place one queen, and then for other queen you can explore possibility that what if I put queen over here, does it attack each other, etc. Right, so this is just a random exercise. Nothing is mandatory unless it is as part of your lab exercise, and we will stop here. Yeah, sorry for a lot of glitches there. I forgot some syntax earlier, so thank you very much.